All right. So actually last time, my Zoom had actually crashed. So that was why there was an abrupt stop. But I think it's better if we just do a part one, two, three series. So this will be part two in the series where I'll be doing guided clustering with Surratt. So we left off with telling the various different sizes, the various different sizes of the data. So now we'll be stashing the quality control statistics. This is a very essential part in the Surratt method. So PBMC. Oh yeah, my mouse was in the way. Sorry about that. So in this, the brackets will basically add columns to the object's metadata. So this is very important, and so that's why we have the brackets there. And so percentage feature set is another function that we'll be using. So PBMC pattern equals, and then so we'll put a caret there, MT minus quotes, and there we go. That should work. So basically the MT with the subtraction started on minus will help us with using the set of genes starting with the MT minus as a set of mitochondrial genes. You can calculate mitochondrial quality control metrics using the percentage feature set function. So that function will basically calculate the percentage of counts originating from a set of features. So earlier you'll remember that we did a create Surratt object. So that is like the number of unique genes and the total amount of molecules, and so that will be calculated when you do that. So now we want to show the quality control metric. So we're going to do this for the first 5 cells, so it doesn't take up too much space, but we can still visually see it. So I'll do pbmc.data and comma 5. So that should work. And yeah, just like that, we get tons of output. So as you see, these dots mean there is no molecule present. We talked about that earlier with the sparse matrix. Next, I actually had in my guide, I'd planned another like visual representation, but I think yeah, we'll just go ahead and do it, but I won't be talking much. Let me just type it real fast. Let's see. You can either follow along with this video guide, or as I mentioned, we have the Word doc guide, which was also very helpful to use. Oops. So 2 plus 15. So n count dot. Oh, yep, I put run. I was supposed to put RNA there. I was going a little bit too fast, so I think it should be good after this. Yep, looks good. So next we'll do a second plot. So in the end, we'll be combining these two plots to create a good visualization. And you'll see that there are subtle differences between the 2 lines of codes I'm typing here. So let me just wait for a little bit, and so see there's still the feature 1 equals n count underscore RNA, and so feature 2. This is where the difference comes in. So instead of putting %.mt, we're doing n feature underscore RNA. Unexpected. Oh, gee. I'm getting all sorts of errors today. So the error was that I put a space in between the 1. So you see there's no error now. And next we're just doing plot 1 to plot 2. And there we go. Here's the magic. And you can see the 2 plots. And Next, we'll just be continuing on with the guide, PBMC subset. Yeah, I'll be writing lines of code and then I'll explain them right after. So equals n feature underscore RNA and greater than 200 and ampersand. So there it is, ampersand n feature RNA. So all these lines of code, logically, they will make sense. So like, and will be like, basic and. So it's good to know basic computational knowledge before jumping into R programming. I recommend you try Python and before you do R. So that's what I actually did. So yeah. Oh my goodness, I'm getting all sorts of errors. So let's find out what the error is. So this is very normal. You'll find like errors like this, but sometimes you can do this. You can copy it and then Google the error and like see what happened there. But in this case, I think it was a simple. I mistyped somewhere. So let's see what that was. Yep, here it is. So instead of putting an equal symbol, I was going a little bit fast and I pressed the minus sign. So fix that. Yep, perfect. So, okay, now I'll provide some explanation. So after you remove all the unwanted cells from the data set, you'll want to normalize the data. So that's what we'll be doing next with the line of code. So we'll be using like, this is what's normally used. It's called log normalize. That's the function we'll be using. So this will normalize the future expression measurements for each cell by the total expression. And then it will multiply this by a scale factor. And the default is 10,000, and then log transforms the result. So these transform values are stored into the PBMC brackets, quote unquote, RNA and PBMC.data. Okay. So now I'll be typing in using the normalize function. So PBMC, put the arrows, normalize data, and PBMC. Yep, you wanted to type PBMC a ton. Normalization method equals, put in quotes, log normalize. Yeah, unfortunately, I made the document in a way that you could not copy and paste the code. So you'll have to type it all, but in one way, it's actually a plus because it gives you some practice and see if perform the log normalization, and you'll see a cool looking progress graph here with stars here. Okay, and sometimes people will think this is a little bit too long, so you can also do it like this: PBMC normalize data, much more simpler. Oh, and the parentheses, much simpler, but it does not allow for like, it offers a readability issue though. So like clarity essentially. So now let's go on. So next we must calculate a subset of features that exhibit high cell-to-cell variation in the set. For example, they're highly expressed in some cells, but they're lowly expressed in other cells. So we'll go on to enter lines of code. So PBMC, we'll be altering it, and so we'll be using the find variable function. So I'll talk about these functions and such later. PBMC, comma. Let me just focus on typing this out. I don't keep on making mistakes. BST and n features equals 2000. Okay. I'll double check. Looks good. Calculates it. Very nice loading bars in a sense. So now we'll be finding the top 10. Oops, there should not be any space. Top 10. Oh geez. Head variable features. me move my mouse so you guys can see features and PBMC, comma, space 10, enter that in. And next we'll be doing another visualization. So like we'll do the plot 1, plot 2 type thing. So the plot 1 is the variable feature plot, and so we'll need to tell you, need to tell what the variable feature is. You'll see in all calling PBMC. That is why we created the object in the very beginning, so we can use it in this way. Plot 2, label points. So we'll be using the function label points, and so this plot equals plot 2. Instead of like typing everything out, you can just do this for ease. And so the points are the top 10. That's why we were writing the top 10 code earlier. So we'll be putting top 10 here, and repel, you want to leave that as true, or no, yep, tree. Okay, so do that. And yeah, it'll give you some sort of message here. You can just ignore that. Plot 1 plus plot 2. Now we'll get to see the visualization here. Yep, just like this. See average expression x-axis, standard variance y-axis. Gives you the specific details right here. Yep. So the top 10 will basically identify the top 10 most highly variable genes. So the last section of the code for creating the plots, the plot variable features with and without labels. So next we scale the data. This is known as applying linear transformation. For this, we must use a function called scale data. So this will basically do three different things. So it will shift the expression of each gene so that the mean expression across the cell is 0. It will scale the expression of each gene, so its variance across the cell is 1. And finally, it will take the results of the stored PBMC brackets RNA, PBMC.data, and it'll take it and store it. So next, we'll move forward with all.genes, row names. As always, I will be explaining it right after I type in the code. Row names, not row name. Okay, yep. It'll show you that it's centering and scaling the data matrix. And as always, this is like multiple lines of code, a little bit more complex, but you can make it more simple by putting PBMC and just doing scale data just like this, and then just putting in the parentheses. But and it'll provide a readability issue or a clarity issue. So what to do with that? So now let me cover over what's happening here. So this will omit the features argument. Through this line of code, the PCA and the clustering are clustering also known as like, and PCA and clustering is like analysis methods. So these results will be unaffected. But the heat map, the do heat map function will require genes for it to be scaled. So that is why we're centering and scaling the matrix here. So after that, we will perform PCA on the scaled data. The previously determined variable features are usually used as an input, but through the use of features argument, you can choose another subset. So next we'll be putting we'll be doing another graph later, but so there'll be 4 lines of code here that I'll be putting before I explain them. So I'll be doing a run PCA function here. Features equals variable features. And then you want to put the parentheses object equals PBMC. And don't forget the second parentheses. There's one here. You got to make sure everything is enclosed. And let that load for a little bit. It'll be running the PCA analysis method. And you can see that it's showing what's positive and what's negative. And so we'll keep moving on. So we can print the PBMC, the print the PBMC. Double bracket that I mentioned earlier, and so double bracket and comma dims DIMS equals 1:5 and so comma n features equals 5. Okay, yep, that gives us another type of visualization in a sense. So viz dim loading. So overall, this is just a basic process. It can be altered in your own way depending on how you require your analysis to be done. So this is a common way to do it, and this is how I would do it. How I did it using my own data sets that I was provided by my mentor. So reduction equals parentheses PCA, and you can see the visualization here. And all these visualizations are very helpful in your analysis. And then dim plot PBMC reduction equals parentheses PCA, and yep, another visualization, a great visualization. So now let me focus on this line of code here. So that code, beginning with print, examines and that visualizes the PCA results in a multitude of ways. These are the multitude of ways right here. And next, we'll be doing the DIM heat map. So this DIM heat map function I will be using will help the PCs to include further downstream analysis. This is extremely valuable for exploring correlated feature sets. So I've actually, in the guide, I've attached a article or something you can read that is interesting regarding this DIM heat map or DIM heat map, however you wish to say it. So DIMS 1, you may recall I was typing something similar earlier. So feel free to rewatch this if there's any trouble. I'll leave my information in the description box so you can reach out to me if you have any questions or such. And yep, this is a beautiful representation right here. This is very commonly seen when analyzing using Surratt. So, and then I'll give you another visualization here. It'll be a little bit different. I don't want to go too much into detail of each thing because it'll take too long. So I'm just briefly covering it. So yep, this is showing multiple different heat maps here. So you can see the yellow, the pink, the dark colors. It can all help you analyze this. So I think I'll stop part 1 right there, and or no, I'll stop part 2 right there, and the next and the final video is going to be part 3. So yep, thank you so much for listening, and I'll see you in part 3.